Hello and welcome to the 44th lecture in the series. Last time I had started with a description of the lead derivative of one vector field with respect to another. So this was done using the flow. So I have two vector fields to start with, x and y. I use the flow of x and actually the derivative of the flow map to pull back the vector field y at some point back to this base point P and then compare with this yp and then take the difference quotient and then take limit as t goes to 0. So this is called the lead derivative of y with respect to x. Even to make sense of this definition, I would of course need to know a few things. That I would need to know things like that phi of minus t composed with phi of t is the identity and so on. So the definition I've given here, one has to do slightly more, look at it a bit more carefully to make sure that everything is properly defined and so on. But all that can be done, and anyway I'm not going to go into details about this. So let me just leave it at this. So the proposition is that the Lie bracket of x, y at P is the same as Lie derivative of y with respect to x at P is the same as the Lie bracket of x. On first sight, this equality is not obvious at all, because when we define the Lie derivative of y with respect to x, x and y seem to play quite different roles. After all, we are using only the flow of x and pulling back y, not the other way around. While in the Lie bracket definition, x and y more or less have the same roles, except that one comes with a minus sign, the other one comes with a plus sign. There are two terms, but the roles are more or less the same. So here, and in fact that's also reflected in things which are obvious for the Lie bracket are not so obvious for the Lie derivative if we don't have this equality. So for instance, the fact that the Lie bracket is antisymmetric in the context of Lie derivative is not clear at all, that Lxy equal to minus Lyx. If we have this equality, then it becomes clear. Similarly, the fact that the Lie bracket is bilinear in the first variable x is not clear in the Lie derivative. So there is something to be done here to prove this, but I won't go into the details of this. Rather, what I want to talk about is in the final topic regarding the Lie brackets and vector Lie bracket and more generally vector fields is the so-called Frobenius. So there are two versions. So the first one is version 1. Here what we want to do is, here again the Lie bracket plays a crucial role in both these theorems, and in version 1 one asks the following question. We know that when we have a coordinate chart, we get a frame on the chart. In other words, we get n vector fields which form a basis at each point in the chart. So we ask for the converse. given n vector fields on a manifold or an open subset of the manifold, it doesn't matter, given n vector fields. So the manifold dimension is n as usual. When can we, and so given this, let P belong to M. Can we find an open set U containing P and a diffeomorphism phi from U to U1 and Rn such that xi equals del by del xi in this chart. So in other words, of course, as usual, del by del xi means del by del xi denotes the pullback under the derivative of phi inverse of the usual del by del xi operators in Rn. So those, can we find a chart so that these vector fields, we are starting with some vector fields, so that this happens. I can write it like this. So the question is about the existence of this diffeomorphism phi. So actually, right, let me be more explicit, i.e. d phi of xi at any point xi at P is del by del xi at phi of P. Well, can we find an open set under diffeomorphism such that this happens in this chart? Right. Now we know that these if such vector fields, note that if xi can be written as del by del xi, then since the del by del xi in Rn commute, this the Lie bracket of del by del xi and del by del xj is 0 in Rn, same thing should happen for these xi's. Then xi xj equal to 0 for all I and j. This turns out to be the crucial thing. So this gives a necessary condition. Not all it's so as an example, it's quite easy to write down two vector fields. So on R2, suppose I take x1 equals, well, I just take del by del x1 and x2 I take it to be some function, let's say a times del by del x1 plus b by del x2. Then the Lie bracket of x1, x2, so here a, b are functions on R2, which I'll choose shortly. So it is again using the earlier notation, it would be del 1 of a del 1 plus b del 2 minus a del 1 plus b del 2 of del 1. This will give me we have done this computation once, but anyway, it's a times del 1 squared plus del 1 a del 1 plus b times del 1 del 2 plus del 1 b del 2 minus this one just gives me only two terms, a times del 1 squared minus plus b times del 2 del 1. Now this thing here will cancel, a del 1 squared will cancel off with this, and b del 1 del 2 will cancel off with b del 2 del 1. So finally you are left with del 1 a del 1 plus del 1 b del 2. All I have to do is just choose a function. So if, for example, if a of x1 x2 equal to x1 and b of x1 x2 is identically 0, then the Lie bracket is would be just del 1 a, which is 1 del 1. So the point is that Lie bracket is not 0. Well, so in particular these two cannot arise as coordinate in particular x1 x2 cannot arise as coordinate vector fields for any local diffeomorphism, locally defined diffeomorphism for any chart. Now, so this is one restriction on x1, x2, that the Lie bracket should be 0. There is another restriction. So this is the first one. The second restriction is that also we know that this del by del xi at any point p in U is a basis for TPM. Therefore, but if these vector fields happen to be coordinate vector fields, then it is necessary that these things xi at p are equal to 1 to n should be a basis. In other words, since there are exactly n of them, the same thing as saying that they should be linearly independent or that they span, either one will do, should be a basis for TPM. So in other words, there should be what we called a frame. So these vector fields should be a frame, should form a frame for an open set, and the Lie bracket, pairwise Lie bracket should be 0. Then at least some necessary conditions, two necessary conditions are satisfied. But the question is, are these two the only necessary conditions for them to arise as coordinate vector fields? The Frobenius theorem says yes, these are both necessary and sufficient. If 1 and 2 are satisfied, should be a basis for TPM. So here for all P in M, 1 and 2 are satisfied, then we can find a chart. We can find a chart u phi around any p in M such that xi equal to del by del xi in this chart. And this is a useful thing to know in various situations. And I should remark that the way the proof of this goes, it's actually uses flows and lead derivatives. It is the proof is and how the Lie bracket comes about is so the proof, this is not even an outline but a very vague sketch of how one would go about trying to find. What one is attempting to do is, so let's say we want to find this. The goal is to define this map phi, find an open set U and a map phi such that this happens. Well, so let's try one thing. So here's the manifold and there's a point P. Now let's take the case n equals 2, two-dimensional. So here I just have two vector fields. So now we know that around P, all integral curves of x1, we can find a neighborhood such that all integral curves around P are defined in this thing, that for at least time epsilon. And similarly we can find by shrinking the neighborhood if necessary, we can assume both x1 and x2 have integral curves defined for some common epsilon, shrinking the neighborhood and taking a smaller epsilon if needed. So we in some neighborhood both integral curves are defined. So one way to find this diffeomorphism would be, so let's call these two as S and T. So this is the T variable, this is the S variable. So what I do is I map this x-axis to the integral curve for the x1 vector field passing through P. So the 0 goes to P, and this part, at least for everything, is defined all the way up to minus epsilon epsilon, here too minus epsilon epsilon. So this part I map to this curve. And now if I want to, the idea is simple enough. Now suppose I want to get hold of other points. So I want to map this entire square in R2 into the manifold. So actually instead of finding phi, I'm trying to find phi inverse. So I'm going to define phi inverse. So first I mapped the central line, which is the x-axis. Now if I want to map another horizontal line, so I have to start at some point here. And again, the idea is to take the integral curve through the corresponding point here. But where should this point go? So I want to send this somewhere. The natural thing to do is just map this y-axis to the integral curve of the second vector field x2. So like this. So this yellow line segment is mapped to, so this is integral curve of x1, and this would be integral curve of x2 with the initial condition that both of them pass through P. once I have the integral curve of x2, I can try to fill out, see where all elements of the square go to, because I just look at the horizontal line passing through that. So then map this to the corresponding, again, integral curve of x1 passing through this point. So this is also an integral curve of x1. So one can certainly try to do that, and one can define this in terms of flows. So I flow along, so if I want to see where this point goes to, I use the flow of for y2 and move here and then move, and then use the flow of x1. Sorry, not y2, x2. Use the flow of x2 to move here, then use the flow of x1 to move here. But a problem arises because here the same in R2, the same point, this red, rather I've already used red, so this green point can be approached, this curve lands me here, or rather I can go like this and go like this as well to the same curve. If my map is to be well defined, then I would be forced to the conclusion that, forced to have the condition that moving along the flow of x2 and then x1 should be equal to moving along the flow of x1 and then x2. This condition that the flow of x1 and x2 should commute, it turns out is precisely equal to the condition that the Lie bracket of x1 and x2 is 0. And the way one sees that is via the Lie derivative. It all ties up very nicely, but the idea of construction of coordinates is rather simple via this picture that I have drawn here. After one shows that the map is well defined, then it's not that difficult to check that this phi actually gives a diffeomorphism from this open square. Phi inverse gives a diffeomorphism from this open square onto an open subset of the manifold. And of course, the original goal of getting hold of xi as del by del xi is automatic, because after all we are dealing with integral curves. So this condition, when I differentiate, so this coordinate vector fields here are going to the standard coordinate vector fields in R2 are certainly going to x1 and x2 here, because we are working with integral curves. Okay, so that is one version of Frobenius theorem. The other one has to do with integral submanifold. So this is the chart version. Version 2. Here we ask the following question. So first let's note that if X is a vector field on M such that xp is not equal to 0 for all p in M, then given p in M, we can find epsilon greater than 0 such that epsilon greater than 0 and a curve sigma minus epsilon to epsilon with sigma 0 equals p, and then sigma prime t equals x at sigma t. In other words, all I've said written here is that we can find an integral curve passing through that point. Now, so what would be, so this is something that we already know. This is not the theorem. So what would be the case? Suppose I have two vector fields rather than one vector field, or rather finite number, let x1, xk be a subset of vector fields, be a set of vector fields on M. Now this condition for one vector field, we had the condition that it's not 0 at any point. We saw that if it is actually 0 at a point, the integral curve through that point is just a constant map. You don't get a one-dimensional, you don't get a curve. So now here, suppose I have this is inside this, be contained in KFM such that the condition that xp is not equal to 0, we'll replace it by, so that one, x1 is linearly independent at each p in M. And now here there's a big difference between this one vector field and higher dimensional case. So the goal is, so here a curve we like to regard as a one-dimensional submanifold. So what the one vector field case tells us is that if you have a vector field which is non-zero, I can find a one-dimensional submanifold which is tangent to the vector field. That's what this is saying. Actually, it's actually equal to the vector field. If you have a bunch of finite number of vector fields, then we want to know when they form the vector space they form at each point. When is it the case that the subspace of that this vector space is actually tangent to a submanifold? So the condition is that such that this happens, and second condition is xi xj at any point p belongs to the span of x1 p etc. xkp for all p in it. Then given any p in M, there exists k-dimensional submanifold S of M with p in S, and the tangent space to S at any point is actually just the span of these vector fields x1q, xkq. So this is, and the submanifold will turn out to be unique as well. This is called the integral submanifold of well, let me integral submanifold of the distribution, that's the technical term, of the distribution generated by x1 xk. So the geometric idea is simple enough. It's just that given, if you are given a set of vector fields, we want to know when exactly they are, and we know, suppose they are linearly independent at each point. So the dimension of the tangent space they span is fixed. We want to know when there is a k-dimensional submanifold. And the Frobenius theorem tells us, I'll end by this, the Frobenius theorem. Again, a necessary and sufficient condition is that, oh, actually I've already written the necessary and sufficient condition. So if 1 and 2 hold, S always exists. You can always find such a submanifold. Okay, so we'll stop here, and in the next lecture I'll talk about introduce differential forms. Okay, thank you.